People are probably still logged in, but I think we can get started. Hopefully everybody can hear me okay. And so we thought it would be a good idea this morning to give you an update on the status of the low-res V1 water cycle model, because we are very close to be able to start the deck simulation for CMIP. So this is a good time to provide a brief update to the entire group of where we are. So the latest version of the model that we have, the code name is Beta 3 RC10. And again, today I'll be focusing only on the low resolution configuration, which is a 1 degree atmosphere, 72 layer, and 30 to 60 kilometer ocean. So with that Beta 3 RC10 configuration, we have a number of recent simulations that we have performed. Most of them were performed just at the end of the NERSC allocation year, because we had an increase in allocation that we wanted to use up. So we have an 1850 pre-industrial control simulation. That one has gone up around 260 years. And we were also able to do something we have been wanting to do for a long time, which is a test historical simulation spanning the historical record as defined by CMIP from 1850 to 2014. And that simulation was branched from the control simulation at year 90. And then starting at year 90, we ran the test historical simulation, and in parallel, we ran the control simulation. And the test historical simulation, as well as the control simulation, use all CMIP6 forcings that have been implemented in the code. In addition, we also performed an CMIP simulation spanning the period 1978 to 2011. This one also has the CMIP6 forcing except for the SSTs, which is why the simulation ended in 2011. Once we have the complete set of CMIP6 forcing, we were able to rerun it and up to year 2014, just like the historical simulation. So first, let me show you another one of those PMP plots that you're probably familiar with. And this is just starting with the evaluation of the atmosphere in CMIP mode. So this is the fixed SST simulation that Cheetah ran with the same atmosphere as Beta 3 RC10. And the first few columns are different versions of E3SM. The first three are E3SM versions V1, and then we have V0, and then we have CAN ESM1 CAN 5, which is very similar to V0. And from there on, you have a set of CMIP5 models, all of them CMIP simulation. So the most recent one is the column on the left here. And then the various rows shows different variables. At the bottom, you have precipitation, short wave, long wave, and so on, all the way to some dynamical variable, wind, V-wind, geopotential. And the coloring gives you the relative performance of the global RMS compared to the ensemble of CMIP5 shown starting from this column to this column. And essentially, bluish color means we are doing better than the ensemble, and a warmer color means we are doing worse than the ensemble. And if you look at the first column here, most of the places we have bluish colors, meaning that the performance of the atmosphere is better than the CMIP5 ensemble. There's a few areas where we're doing a little worse, and the most significant one is the geopotential height, 500, which is something we have been struggling. You can see ever since V0 has gotten better, but it's still slightly worse than average. So that's the performance of the data, very much in line with previous versions that we ran, and very good starting point for a couple models. Now, moving on to the actual historical simulation, I'm going to start directly with the figure that everybody has been waiting for, and one of the reasons why we are doing the historical simulation. So this shows the global mean surface air temperature anomaly, the evolution of the model compared to 3 observational data sets. So the model is in red. So this is beta 3 RC10 in red here. And the 3 observational data sets from NASA, NOAA, and Hadley Center are in pale colors underneath there. Just a little bit of background for the model. There's a couple of manipulations that needs to be done to the data to be comparable to the observation. One is to remove the drift of the control simulation. Right now, in this version, the model is drifting warm a little bit. So I computed the linear trend of the drift, and I removed it from the time evolution of the historical simulation. I'll be talking more about the drift a little bit later. The other aspect is that the global observational data sets are only provided as anomalies. So you have to normalize everything with respect to a certain period. And here I chose basically the beginning of the record for all the observational data set. I chose 30 years, which is pretty standard period for computing anomalies. So I chose 1880 to 1909. So all 3 lines are normalized with respect to 30 years here. So their average over those 30 years here is identical and 0. That the anomaly period you choose actually does make a difference because it ends up shifting the model compared to the observation up and down a little bit. So it can be somewhat misleading depending on what period you choose. So the actual evolution of the model here in red. So the good news is that we have a reasonable warming. If you look at the early period compared to the 2000s, we have about the right amount of global mean surface air temperature warming. However, you also see that we have some challenges. In particular, it seems like the model doesn't really warm until the 1980s. So it stays rather flat here, probably more so than the observation. The observation seems to have a trend here. And then in the 80s, the model seems to warm and actually appears to be warming faster than the observation. So even though we capture the change between 1880s and 2000, the actual evolution is a little bit off. And this will probably be a subject of further investigation in the phase 2 of the proposal. It is probably related to the fact that we have a model with a very strong aerosol indirect effect, so that may prevent some of the warming here when the emissions peak. And it's possible that is also related to the fact that we have a model with high sensitivity, which could explain maybe the steepness of the slope in the later period. But this is subject to more investigation and not something that can be done in a matter of weeks. We did do one test where we switched the aerosol emissions, only the aerosol emissions, back to what we were using before. So this is similar to CMIP5 aerosols. And that's the blue line here. We started that simulation in 1930, and because of the emission stop around the year 2000, we only ran a sub-period of the historical. And you can see that the blue line and the red line are not dramatically different. Both of them show relatively little warming until you get to the 80s. So we don't think that the relative lack of warming in the 60s and 70s and 80s is related to the CMIP6 aerosol emission. Now, this is most of the figures I show you from now on are figures from the historical simulation. And this is the sea surface temperature bias compared to the observation. And the model is 1979 to 2001. So this is recent days. So this is the later part of the historical simulation. compared to observation. Not exactly the same period. This is something we'll have to fix in future versions, but comparable period. And you can see the biases in SSTs, fairly typical of what we have seen before in the control simulation, and also typical of many climate models. Cold North Pacific, cold Labrador Sea, warm bias along the continent there, warm bias over the Southern Ocean. The mean bias is very small, minus 0.04, so this is very good. We have managed to stay in line with the observation, and the RMS is around 1.09, 1.07, which is also probably not, it won't be among the best CMIP model, but it's definitely a good value. Some plots from sea ice concentration, Northern Hemisphere, summer and winter. We have excessive sea ice in the winter in the Labrador Sea, not surprisingly. This is related to the cold bias we saw, and a little bit of too little sea ice in the summer, as seen by the blue areas here. And this is sea ice concentration summer and winter for the Southern Hemisphere. Generally speaking, a little bit less than observation. Blue means you are missing. We don't have enough sea ice. This is the Merc, the strength of the Merc, which is an important metric of the ocean circulation.
Yeah, I'm leaving in like 1 minute. I was just... Okay, then. Oh, by the way, I talked to Barry yesterday.
Could you please mute yourself if you're not, Chris? Thank you.
Thank you. All right, so this is the strength of the AMOC simulation over the historical period. The value seems to be hovering around 12 or so, probably lower than we would like to have, but I'm hoping this is still considered to be acceptable. I think the observation is more around 14 or so, but we have seen both in the control simulation and in the historical simulation, we tend to see lower values. Now showing you a couple of figures from the atmosphere. And for this, I will show you both the figures from the CMIP simulation as well as the figure from the historical couple simulation. And I have selected the same period, 1979 to 2011. So this is the top of the atmosphere radiation, the observation from Cirrus EBAF. And then the plots on the right are the difference between the model and the observation. The top panel is from the CMIP simulation, and the bottom panel is from the historical couple simulation. And you can see overall the patterns look quite similar, which is reassuring, meaning that the SSTs are still reasonably close to what they were in CMIP. And the radiation balance is almost right on target for CMIP. We are off by 0.03 compared to the Cirrus EBAF observation. And they're also quite close for the historical simulation. We are slightly lower than the 0.8 from Cirrus EBAF, but this is not a worry. There's some differences. The most prevalent one are further degradation of the stratocumulus when the SSTs are interactive compared to fixed SST. This is rather expected because we develop a warm bias and feeds back into the stratocumulus, and also some degradation over the tropical area here compared to the CMIP simulation. Now this is looking at the same top of the atmosphere, but only the cloud forcing. Excuse me. Again, quite similar picture between CMIP and coupled, with degradation over the tropical ocean and over the stratocumulus in the coupled mode, and also a degradation of the RMS from 10.3 to 11.4. Looking only at the shortwave cloud forcing, very similar picture as the net. The most prevalent errors are the stratocumulus regions here, and they appear already in CMIP mode. This is something we have known for a long time, that we have those biases. In the tropical water, you see also some errors developing, and you see they are related to the SST and the double ITCZ. The long wave cloud forcing changes a little bit more between CMIP and coupled, and this is related to the fact that the long wave cloud forcing is strongly correlated with the precipitation, and I'll show you later the precipitation does change more because of the feedback with the SST. Overall, we have a bias in long wave cloud forcing. It's similar in magnitude between CMIP and coupled, and the RMS degrades a little bit, and mostly the changes are here in the warm pool region and the tropics. So this is the precipitation, showing the actual precipitation here on GPCP observations, the CMIP precipitation and the precipitation from the coupled model. And there on the right, showing the difference between CMIP and observation and coupled and observation. So the most striking feature, of course, is that in coupled mode, we see a clear signal of a double ITCZ, the areas of excessive precipitation here around the equator, and you see it here as well by SPCZ that is too strong and too zonal here. So that translates into the bias here. Another bias that develops in the coupled simulation is the excessive precipitation over the maritime continent here that we don't see in CMIP. The Amazon dry bias exists in CMIP, but it does get worse in coupled mode. And that's also very typical of coupled model. The double ITCZ, the Amazon, those are fairly standard biases that most coupled models struggle with. The RMS is rather good in CMIP, 0.94, and equates to about 1.14 in coupled simulation. Now, ENSO, NEO 3.4, index, time series, and spectrum. As most of you know, this is something that E3SM has struggled for a very long time until there was a breakthrough by the ocean team, and they were able to correct some of their transfers in the ocean, and that led to substantially better ENSO. And that is still the case. We have an ENSO, which is great. For a long time, we didn't have any. And if you look at the spectrum, it's actually too strong now, especially too strong and a little bit too short in period here with a peak around 3 years. And this was the observation, the peak should be more spread between 6 and 3 years. And we tend to have a strong peak here at 3 years. But this is much, much better than what we had before. For a long time, we thought we would have a model without any ENSO. So this is a real success story here from the ocean team. Now going on to the controlled reef simulation that I mentioned earlier. This simulation was started somewhat hastily because we wanted to use the time that was expiring on Earth allocation. So we didn't have time to run the control simulation long enough and fine tune it. So as a result, the Beta 3 RC10 shown in red here has a drift in the global mean surface temperature. And this is the evolution of the control simulation over the 260 years. And then I put a linear drift here over the last 200 years or so. And you can see that the model drifts warm fairly significantly at more than 0.2 Kelvin per century. And that is a little bit too much if we want to run a control simulation of 500 years or more. So after the historical simulation was done, I also started efforts to try to reduce the drift, and I'm doing that by retuning one single parameter in the atmosphere, and that parameter is cloud C14, which directly controls the low clouds and the shortwave reflection. And I made a number of attempts since at reducing the drift, RC11, RC12, RC13, and you see that it's actually not linear because I was hoping that RC12 has basically the same change as between 10 and 11, and by my calculation it should have been flat, but it turns out that the impact doesn't seem to be linear, so RC12 actually overshoot it and turn it to drift cone. The one I'm currently running is RC13 here, which I think looks more promising, even though it's not obvious from the linear trend here because that is just too short a period. So I'm hoping that RC13 or maybe one final tweak will give us a control simulation that drifts a lot less. I would like the drift to be substantially less than 0.1 Kelvin per century so that we can run 500 a year without having to worry too much about the drift. In terms of global mean surface temperature, we are roughly around 13.8 degrees Celsius. And if you compare to, this is a figure from Hawking and Sutton comparing 42 CMIP6 historical simulations. And you can see that most models are around between 13 and 14, maybe most of them around 13.5. So if we are around 13.8 or so, we will be somewhere here, which is where most of the CMIP6 model, CMIP5 models are, and this is close to the actual observation. When you get some warming, you get to the actual value here. So I think we're in a good shape here. You can see so that some models are really way off at almost 12 degrees or 15 degrees. So if we can stabilize the drift around this, we will be in a good shape for the control simulation. And this is the net T-wave flux at the top of the atmosphere for those simulations. And average, the horizontal line shows the average over various periods. So beta 3 RC10 had an average of about 0.18 watts per square meter, so close to zero, but not exactly zero, and that was enough to close the drift. And then my various attempts here, 0.06, going slightly negative, and then going back to very close to zero, 0.01. So it looks like the good news is that if we can stabilize the drift, we may also end up with a net radiation at the top of the atmosphere that is very close to zero. And that would be a reflection of the model that conserves energy well. Because this is not necessarily given. There are models where they need a significant imbalance at the top of the atmosphere in order to minimize the drift. So this is good news. We may be able to have a stable simulation with near zero imbalance in the pre-industrial. So now moving on to the simulation plan. So most likely this model RC13 or maybe one final tweak will be used for the DEC simulations. And I should mention that that tiny retuning that I'm doing really doesn't change anything when you look at the climatology. So if you look at the figures, they will all look very similar to RC10. This is just changing the top of the atmosphere by less, a tenth of a watt or even less. So the plan is to do the DEC simulations before the model is officially released. That means running approximately 1,300 years in a few months. And the key simulations are control simulation, which needs to be at least 500 years long. Two idealized simulations, one about quadrupling of CO2 and one 1% per year CO2 increase. Both simulations are 150 years in length. And then finally, historical simulation. Each one 165 years from 1850 to 2014. And we really need to do more than one ensemble member. So we're hoping to do at least 3 ensemble members. And then in addition, there is a CMIP simulation that is required. That's only 30 or 40 years. So those are the simulations that once the model is frozen, we need to perform rather quickly. After that, before the release, supposedly we should also publish the data, write a paper, and then release the model. So this is a lot of more work ahead of us. I think it is possible to do that, but there is not much room for problems. So if we discover something wrong with the model that we did not see before, if something goes wrong with the computer platforms we are using or other things, we may not be able to complete the simulation in time. Another challenge is that because of the constraint, we cannot do a clean initialization. And a clean initialization would be basically starting from limiters of present-day world ocean and then spinning up the model with a GKs and then doing a long spin-up in the couple mode. But we cannot afford to do that because it probably would require an additional at least 300 or 400 years. And we get maybe 50 years a week. So if we wanted to do 400 years of additional spin-up, that would be 8 weeks. And that is just sometimes even more. That is completely impossible. So the backup plan is to reuse initial conditions from previous couple simulations. And this is what most modeling centers do anyway. So I think we won't have any problem to justify it. And this is likely the series of simulations that we will be using. And that's what we have been using in the past. So I went back to Confluence and I traced back the history of the initial conditions that were used for beta 3 RC10. And the history, I think, starts with a few months or maybe a few days of just standalone MPass Ocean. I need to verify that later. Followed by 10 years of a GKs, and then 50 years of a couple simulation, that FCT2 simulation, which was sort of the breakthrough simulation that was run by John on Anvil. And this is the one that included significant improvement in the ocean, and that led to the appearance of ENSO. That simulation was used as the basis for the 200 years of beta 3 RC10. And then as well for and then we used for my retuning attempt of beta 3 RC13. So most likely what we will do is we will take some initial condition somewhere into beta 3 RC13 to use for the first initial condition of the deck control simulation. And we can explain that when we publish. This is not uncommon. So before we get to the point of actually starting the deck, there's a few more things that have to happen in the next few days. We still have to make master reproduce beta 3 RC10 before B. There was a few issues because that was based on a branch and there was some non-BFB changes that were on master that were not in the branch. I think this is on the way of being resolved. Then Rob wants to create an actual tag, so we have a reference code on master for the beta 3 simulations. And then there's some bug fixes that are deemed necessary that are non-BFP will go on master. And then we will need to finalize the tuning. Hopefully beta 3 RC13 is good enough. After that, there will be a soft code freeze. So there won't be any more non-BFP changes on master, at least related to the CMIP6 simulation for the water cycle, unless there is a serious bug that is discovered. But otherwise, we should stay with only BFP changes. And hopefully we can create a tag at that point and then start the deck simulations. So this is my last slide regarding the actual execution of the deck simulation. There's a whole infrastructure that is now mostly in place. And this is just a brief overview of the various pieces that are needed. So we'll be running the deck here, the various control, historical, idealized simulation. So the whole running the model is performed in CMIP utilities. The code will be, as I mentioned, we'll make sure we'll get the code from master, from a tag, and the setup of the experiment, we're going to use the HANACME script. So we have some provenance of how the simulation went on. There has been a lot of work on putting the CMIP6 concept in the code, so that is mostly ready. The simulation, we are planning to do them on NERSC Edison. And then, so the output will all be on the scratch phase at NERSC. We will be using the short-term archiving to organize the output better. And from there, Sterling Baldwin from the workflow has been working on an automated tool to post-process the data, which is called the process flow. That tool automatically transfers data to Acme 1, which is the machine we will be using for post-processing and storing a large portion of the output. It generates climatology time series, as well as calls various diagnostic packages, A prime, Acme diag, and path analysis. And then further on from that data, the plan would also be to run CMOR and then publish to ESGF. This in black here is basically working today. The CMOR and the ESGF phases are still under development, but they can happen later on. There should be enough space on Acme 1 to store all the data we need. We will also be archiving the data to HPSS, so we can go back if something is missing or something happened. And I've been working on a simple utility to do that. And the plan is to archive first at HPSS and maybe also have a backup archive somewhere on a different HPSS, so we will have two backup of the data. So I think this is mostly in place. The tools are mostly in place, and once the code is ready, we should be able to get started with the control simulation, running it for 100 or 200 years, and then follow on with the historical and all the other simulations. So I'm hoping we can complete everything in time. So that's all I have for today. I'll be happy to answer any questions if you have.
So it's quiet. I have a couple questions. What are the ideas for the bias and the geopotential height?
We think it's related to bias in the temperature profile in the atmosphere, in the troposphere. I think this is something that we should look at more carefully in as we prepare V2. Understand what causes them and what we can do to reduce them.
So I have a question too. So Chris, do you know why our simulations using the CMIP5 versus CMIP6 emission data seem to be about the same, whereas for NCAR they seem to make a big difference? Is that the case?
That's my understanding as well, and I don't have an explanation. That was one of the motivations for doing that test I did.
Yeah, interesting, yeah.
As far as the aerosol effect is concerned, it seems that the hemispheric distribution of sea surface temperature bias, or was that surface air temperature bias, is also consistent with a strong aerosol effect in the late part of the century. Yes? it's cooler in the northern hemisphere and a little too warm in the southern.
Mm-hmm.
Right. Yes.
When I looked at those simulations, that's when I came in. The temperature seems to catch up after 2010 or so. Is that do you know how come it caught up if there was a cooling before, or am I mistaking something?
So yeah, the temperature catches up here.
Yeah.
So here we have.
Go ahead.
We probably have a lack of warming here because of strong aerosol cloud interactions that are probably producing too much cooling. We also have some volcanoes here going on at the same time. So some of the sharp drops you see are related to volcanoes. And then the steepness here, so it's clearly steeper than in the observation. And that could be related to could be just the fact that the aerosol indirect effect is too strong, so it delays, it prevents the warming here, but as the aerosol loading diminishes in the 90s, then the model catches up. So that's one possibility. The other possibility is that we also see a signal of the sensitivity of the model. So the sensitivity of the model is how much the model warms for a given forcing, essentially. And we know from about a year ago, we did a test about 4 times CO2 simulation, and we see that the model was a very high sensitive model. So that could also explain the catching up here.
Thank you.
I think there's a lot of interesting things here to study, a lot of science and analysis that is probably worth pursuing to understand this, and maybe in a future version of the model to make it more realistic.
Mm-hmm.
Could you say a little bit more about the ENSO as it is right now? It almost, I mean, I'm not an expert at this variability indices, but is it almost too strong now? It's very high frequency, but.
Yeah, the high frequency may be slightly too strong. Now there's quite a bit of variability. So this is I only showing here the observation for the full record of the Hadley SST. We also have a plot showing the more recent period, the last 40 years or so, and the signal is much stronger. So this line here would be a little bit higher in recent days. Now this is for the entire record as well, so it is stronger than the observation. It is also stronger in the historical simulation than it was in the control simulation. And Rich Neal actually warned us that would likely occur because as the model is getting warmer, and so can also get stronger. This is something they have observed, I believe, in CSM.
Mm-hmm.
So it's rather ironic. We may actually have an ENSO that is too strong.
I know you're in the process of analysis. Have you looked at PDO and other modes of variability too?
No. I'm always looking for volunteers to look at the data. So all that data is available on Earth. The simulation are documented on Confluence, and from the pages on Confluence, you should be able to find where the data is on there.
Mm-hmm. Hopefully you'll get some quickly.
So why Edison?
Why Edison?
For the deck, yeah.
Yes.
Is that? I know it's faster, but it's faster.
It's faster than. It's a good compromise between the size of the machine and the speed of the machine. Yes. Anvil would be too small. Core KNL is not fast enough for the locals. Core as well would probably be slightly faster than Edison, but Core as well is small, so we may struggle. And, so that's why Edison. And the other machines, Oak Ridge and Mira, are just not appropriate for low resolution models.
This is Rob. I thought when we doubled the size of Anvil, we were able to get the same years per day as Edison, like order 10.
We might be able to, but we need to be able to, when the deck is running at full speed, we may have up to 6 concurrent simulations going on. And I think we would take the entire Anvil to just do 1 simulation at 10 years per day.
Right, but will those 6 all be competing with each other on Edison? You should put one of them on Anvil. That should benefit.
Yeah, I guess from the NERSC point of view, you just want to make sure a big enough chunk of your allocation is on Core relative to Edison. I'm assuming that's the case. Over the course of the year, or at least.
So Core KNL is really better suited for the high resolution model. So we could definitely do some high resolution simulation on Core KNL over the course of the year, and given the cost of the model, we could burn a substantial portion of time there if that's needed. So I don't hear any other questions. So thank you everybody for your time. As I mentioned, the simulation output is available, so everybody is welcome to look at it. And if you have an analysis you would like to share with everybody, you could ask for an all-hands presentation, or you're always welcome to present something during a water cycle couple simulation telecom.
Hey, Chris, thank you very much. It's a really clear presentation. Yeah, thanks.
You're welcome.
Yeah, thank you, Chris. Thank you, Chris.
Bye.
Bye.